All right, hello everyone. Welcome to another AP Chemistry lesson. Today we are going to be covering Unit 1, Topic 3 of Atomic Structures and Properties. One of the main objectives for this unit is to use chemical formulas to identify substances based on their unique combination of atoms. Okay, and what we're going to be covering today are the following. Understanding that the ratio of the masses of the elements in a pure sample of a compound is always the same. Okay? And this should be review, but we will also revisit how to determine the empirical and molecular formulas. Okay? So one of the most important things about dealing with pure substances and chemical formulas is understanding mass percent composition, which is defined by the mass of each element present compared to the total mass of 1 mole of compound. Okay? And it's a very simple equation to determine mass percent composition, just like if you were calculating the percent on a quiz or an exam. Okay? The mass of a part of the compound divided by the total part of the compound. In this case, we're dealing with mass. Okay? One of the things that you need to be given to determine mass percent composition is molecular formula. Okay, and in this lesson, we're going to kind of go forwards and backwards. We're going to require something that determines where we need to know the molecular formula, and then at the end of the lesson, we're going to be determining the molecular formula. To determine the mass percent composition, in addition to knowing the molecular formula, we have to know the mass of each element, whether directly or indirectly. Okay? And because we know the molecular formula, we can also determine the molar mass of the compound. So let's look at an example. Okay? Carvone is an aromatic substance found in caraway seeds. Okay, and it has the molecular formula of C10H14, 1 oxygen. Okay, what is the mass percent of each element in this molecule? Okay, you'll notice, okay, it's asking for mass percent composition, but we're not given any masses. Okay, which means that we can make one important assumption. Okay, that we have 1 mole of this substance. Okay. Because if that's the case, we know based on molar ratios and stoichiometry that for every 1 mole of compound, we have 10 moles of carbon, 14 moles of hydrogen, and 1 mole of oxygen. So it doesn't necessarily give us the mass, it just gives us an initial quantity, theoretical quantity of each element. Okay? Because as we learned in topic 1, we can take a quantity of a substance and determine the mass of it. Because if I have 10 moles of carbon, I can use the molar mass of carbon to figure out that theoretically this substance has 120 grams in 1 mole of the substance. Okay? So go ahead and do the same thing and determine the gram amounts of hydrogen and oxygen. The molar mass of hydrogen is 1, so that makes it an easy 14 grams. Okay, the molar mass of oxygen is 16. That gives us a total of 16 grams of oxygen. Okay. If we combine them, we have a total of 150 grams of, not carbon, but of carvone. Okay. So now that we know the total mass and the individual masses of the elements, all we have to do is divide each individual mass by the total mass multiplied by 100, and we get the following percents. Okay, 80, 9.3, and 10.7 respectively. Okay. All right, now, with pure substances, okay, molecules will always have the same fixed composition of elements, always. Okay? And an example is what we just saw is carvone. It will always have 10 carbons, 14 hydrogens, and 1 oxygen. It will never deviate from that. As a result, the percent composition will also always be the same. It will never deviate. Okay? So if those percentages change, okay, that tells you that whatever substance that you have, it is not pure carvone. All right, so different compounds can have the same mass percent composition, and this is directly related to the molar ratios or the subscripts of elements in a compound. Okay? And a prime example of this is NO2 and N2O4, both completely different compounds. However, if you reduce both of the subscripts to the simplest ratio, they are 1 to 2. Okay? Which means if we figured out the mass percent composition, they would each have roughly 30% nitrogen and 70% oxygen. Okay? Now, if we combine these two in a beaker and you measure the mass percent, you would never know that you would have two different compounds in them because they have the same mass percent composition. So we would need to know some additional information in order to differentiate or know that that is not a pure substance. Which leads us now to talking about empirical formulas. Okay? If you notice on that last example, NO2 and N2O4 have the same molar ratio of elements. Okay? And they also had the same empirical formula, which is the lowest whole number ratio of atoms in that compound. Okay? Here are some other examples: benzene, ammonia, ribose, glucose. Okay? Their molecular formulas are different, okay? But in some cases, the empirical formula can be the same. Okay? So the empirical formula for benzene is taking the reduced ratio 6 to 6 to 1 to 1. Okay? In some cases, a molecule will have the same empirical formula as a molecular formula. Okay? Two different molecular formulas can actually have the same empirical formula, much like ribose and glucose. What we're going to do next is how to determine empirical formulas, simply knowing the mass percent composition. Okay? And I try to break this into a bunch of simple steps. Okay? First one is we're going to assume that we have 100 grams of our molecule. Okay? Convert grams to moles, divide by the smallest number of moles, and then use those mole ratios as subscripts. Okay? So let's look at an example. Okay, what is the empirical formula of a compound that contains a certain percentage of potassium, hydrogen, phosphorus, and oxygen? Now remember, those subscripts that are in the formula are a molar ratio. Okay? So we need to figure out how to go from mass percent composition to those subscripts. And first, we assume that we have 100 grams of sample, because that makes converting percentages to a quantity of mass very easy. Okay? So those are the masses of our elements, okay, which allows us now to convert those to moles using the molar mass of each element. Okay? And I get the following, following the rules of significant figures. Okay? Where a lot of people make a mistake is assuming that these values are the initial subscripts, but they are not. They are just the mole values of those elements. Okay? What we need to do next is actually divide each of those by the smallest molar amount to get a ratio. And in this case, 0.734 is the smallest, so when I divide all of those numerical values by that value, fingers crossed, hopefully I get something close to a whole number. Okay? And I pretty much do. 1, approximately 2, 1, and 4. Okay? There is a rule of if it's not, then we have to keep increasing those values by increasing integers until we get whole numbers. Okay? But we'll rarely see that. Okay? So here I have my empirical formula, KH2PO4. Once you know the empirical formula, you are now one step closer to determining the molecular formula. Because determining the molecular formula requires knowledge of the empirical formula and its molar mass, as well as the molar mass of the molecule based on its molecular formula. All right, so we'll end today's lesson with determining the molecular formula of ascorbic acid, otherwise known as vitamin C. All right, we know the empirical formula All right, but you can imagine I can give you the mass percent composition and determine the empirical formula separately. We're going to shorten this up. I'm also given the molar mass of the molecular formula, which is 176.1. What is the molecular formula? Okay. Well, what we need to do is determine the molar mass of our empirical formula. So go ahead and do that, which is about 88.0 grams per mole. Now, the difference between a molecular formula and an empirical formula is a ratio. And we can get that ratio, or that integer, by dividing the molar mass of the molecular formula divided by the molar mass of the empirical formula. So 176.1 divided by 88.0 gives me roughly 2. Okay. So what I'm going to do with that 2 now is factor that through my empirical formula and multiply all those subscripts accordingly. And I get my final molecular formula of C6H8O6, which is also, this is what the structure of vitamin C looks like. All right, so hopefully a majority of that was a review. Thank you for your attention, and we'll see you in class.